Has everyone filled out the attendance? Yeah, I'll just leave it there. And here's the schedule for today. So, yeah, I'll run over the course structure again, but at this stage, everyone should be pretty familiar with it. Yeah, and then I'll run over dynamics quiz question 2, because I'm sure a lot of you have questions about it. I think some of you came at the end of the dynamics quiz and asked me about it, but low-key, I gave you the wrong answer. So I'll actually run through it properly this time. Yeah, and then general plane motion we'll talk about first. So then we're going to be diving into rigid bodies. Velocity dynamics is basically the first part of rigid body kinematics that we explore. And then after the break, we'll do acceleration dynamics as well. This is notoriously the hardest part of the course. So yeah, look forward to that. At the very end, we'll also do a frame question, because essentially frames are out of scope for your statics midterm, so I didn't cover them. Oh, well, we did a question, if you remember, for the statics midterm, which was the first question, which had a frame in it, but it was just simply finding the resultant moment and the resultant force at the support. But what we're going to do for the frame question this time is we're going to draw the bending moment diagrams overlaid on the frame and the shear force diagrams and things like that. Yeah, so basically, yeah, we'll just get started. So here's the course structure. So yeah, this whole thing should be pretty familiar with you now. We're still up to dynamics, but we'll jump back at the very end to frames and explore like the bending moment diagram stuff. We're going to be doing the kinematics of rigid bodies, which I'll explain what rigid bodies are in a second. Kinetics is out of scope for the civil school. Remember, that's like Newton's second law, that kind of stuff. And yeah, in other schools like the mech school, you'd be covering like Newton's second law, but for rigid bodies, which I actually like that topic more than the kinematics topic, to be honest. I think it's kind of cool, but like, anyway, we don't get to do it. Yeah. Any questions about the course structure? Where's my pen going? I gotta find my pen for my tablet, so just chat between yourselves until I find it. Fuck.
Going on the my experience.
Facts.
Does anyone actually do that? They just always remind you of who do it. Oh, that's just what's the news? What's the latest? And you walk into the house present. It's good. What do you get for shot? Oh, I know
The fuck?
What do you say?
Their lineup of games they got to play. They only have to play like
So easy.
the top
So
teams.
It's so
They only play Panthers and Broncos.
Huh. Interesting. Oh,
Oh,
found it. Okay. Sorry, continuing. All right. So let's look at the more detailed version again of the course outline. So we've kind of covered all this stuff. This was all the stuff which was involved for like the dynamics quiz, right? That's all the particle stuff. Now we're going to be doing rigid body kinematics, which involves a lot of relative motion. So if you study relative motion for the dynamics quiz, that's coming back. So yeah, it's not for nil, you know what I mean? And I'll be teaching you the IC method as well, which is the instant center of rotation. Again, yeah, rigid body kinematics, not in the civil school. Okay, let's talk about the question 2 of the dynamics quiz, right? So let's just talk about this. Sorry, to bring back the trauma, but let's talk about it theoretically, right? So firstly, are the objects A and B moving together in terms of its velocity? So yes or no?
No.
Yes.
Yeah.
They're
I think they're moving
connected
together.
by an inaccessible road.
But Did they have the same mass?
No.
No.
Very good. Did they have the same acceleration?
No. They can't.
They don't. So they can have the same velocity, but not the same acceleration. I'll just keep this one. Think about this equation and what it means. And think about mass in general. We think about mass in terms of like the units, right? Kilograms, but we don't often think about what that means. It's a resistance to force in the expression of acceleration, if that makes sense. So if something's heavier, it's harder to accelerate, right? If something's lighter, it's easier to accelerate. So these values for acceleration can be different for the two objects, even though they're moving together, the same velocity. Does that make sense? Yeah. Think of mass like a resistance to force, I guess. Yeah, kind of. Anyway, yeah. Might take a second to wrap your head around that, but that's... So you can't think of these two objects like they're accelerating together, or yeah, at the same rate. You know what I mean? Okay, so the way that we solve this question is we can do a bunch of free body diagrams to analyze the forces, right? And the first one we can look at is this one. This is not necessary to draw, but I'm just going to draw it so that you have a good understanding of what it means, right? So this is the pulley, right? And we talked about how two different pieces of rope, right? So like that's one rope, and here's another rope. They can actually have different forces if they're different ropes. But if they're the same rope, they have to have the same and like consistent tension, right? So essentially if we take the sum of the forces, right? Okay, that can equal MA, whatever. But here's where I'm gonna update what I said the other time about pulleys, right? Last time I said they're in a static equilibrium because the velocity is constant, which might be true, but it's because the assumption of mass, these pulleys being massless, I want to say, is the reason why some of the force is actually zero in the y direction. We take this as an assumption for our pulleys. And so if we take the upwards direction, for example, as a positive direction, right, we can see that, you know, t plus t minus 2t, yeah, we have, that's basically why this is 2 times as much as those tension forces going upwards, right, in that direction. Okay, but again, you don't need to draw that free body diagram, that's just more to explain where that comes from. The next one is the free body diagram at B, right, so B is this box here. So we've established that we have 2t going up like that, and it's connected to this box, right, which is has a mass of B, right, and gravity, right. So this is our weight force of B. Okay, let's draw the diagram for A next, right. So here I'm looking at the diagram for A. Okay. Basically, maybe I'll color code it. So we know that that force there is T, not 2T, right? Or actually, there's 2 ways you can do it. You can call these each T and this 2T, or you can call this T and these T over 2. Those are the 2 ways you can do it. But for this convention which I've written down, right, this is being pulled to the right at T, like with a force of T. Let's think about the other forces here, right? We've been told in the question that it's frictionless, right? Which means that we won't actually have that friction force opposing the motion of the motion of the box, right, in the horizontal direction. And we can actually also draw out, if we like, the forces in the y direction. But to be honest, it's not going to tell you anything important, because we have our weight of the box going down, right, and we have the normal force that corresponds to it, but it's in static equilibrium because the box isn't accelerating up and down, it's only accelerating to the right. Do you know what I mean? And these numbers would only be useful if we're also calculating the force of friction, because remember, we calculated this way. We calculated the weight, which corresponds to the normal force, which corresponds to the friction force. But we don't care about the friction force, so there's no point in drawing these arrows on. we're considering these arrows, right? Does that make sense so far? Okay. Okay, so let's actually do some calculations. Let's look at the sum of the forces over here, right? And yeah, for this one, we can't assume it's in static equilibrium because it's moving, right? So we have to equate this to F equals ma, right? But we do know that the only mass we're looking at in this free body diagram cut is the mass of B, because the rope is weightless as well. That's another one of our assumptions. Did I call this A? Oh no, I'm tripping. Okay. And yeah, this acceleration is unique to the object B as well. So we're going to call that mb multiplied by ab, right? Okay, now for the right hand side, we're going to actually look at the forces on the diagram. So all here, let's call this the left hand side. This is just saying the net force we express as m times a, right? That's Newton's second law. And now we actually analyze the forces on our drawing, right? So m times g minus 2t, right? And we can actually calculate this fairly easily because we know the mass is 300, right? 300 kilonewtons. So this ends up being this when accounting for gravity, right? But we don't know what t is, but that's fine. So we can leave t as an unknown, but we can also say we know the mass of B is 300, right? Okay, sorry, I'm going to bring this up here. Let's do the sum of the forces. I like to do the sum of the forces in the direction of motion, by the way. So if you do the sum of the forces down instead of up here, in this particular case, then we know that the acceleration will be, the net acceleration is positive. That's why we want to sum the forces in the direction of motion, right? So the motion is going to the right, so we're going to point the sum of the forces to the right. Okay, so the only force here is T, right? So simple as. If there was friction, you'd subtract off the friction that way, right? But yeah, we know the mass is 100, right? So here's one expression that we can have, right? And let me just rewrite all this stuff here into a separate line. 300 AA is equal to 2943 minus 2t. Oh, my bad. Let's call that expression 2. It's expression 1. Yeah. Okay. Now here's kind of something which I didn't directly teach, so it's kind of on me. But there is a third equation you need to be able to solve this simultaneous equation, because if you look, we have. Oh, did I write that down wrong? Yeah, that should be B. My bad. Yep, sorry, that's AB. We have three unknowns, right? We don't know what the force in the rope is. We don't know what the acceleration of B is. We don't know what the acceleration of A is. So we need a third equation. And that third equation is saying this. So this is actually a byproduct of the mechanical advantage in the rope. It's kind of on me. I didn't really teach that very clearly. But yeah, basically it's saying that the acceleration of A, right, this one, is 2 of B. So that's AB, it's AA, AA is 2AB, right? I don't know how to explain this, but yeah, think about the mechanical advantage of the rope, and it's this way around. So it's like a ratio, I guess. Okay, and then that's our third equation. And since we have 3 equations and 3 unknowns, then we can solve it simultaneously, right? So the answers which would have gotten you full marks is this. So we don't need to solve for t, basically. You can solve for t. it allows you to solve for t. But yeah. Okay, any questions? Yeah.
If I was to do t equals negative 100a, and then do my box B as 2t minus 2143 equals AB, should it work out the same?
Oh, so
I take my positive as being up instead of down.
Yeah, I think it's because you probably pointed this way, right?
Yeah.
And so you would have gotten negative.
Yeah.
I'd have to do the calc, but I'm pretty sure the magnitudes would be the same.
That's what I realised.
I'm not sure off the top of my head. But basically you want to look at the question and be like, okay, in my head, which way are all these things moving? And you want to point the sum of the forces in the direction in which it's moving. Yeah. Because then you'll end up with a positive of this, essentially. But if you assumed up was the positive direction, you could have gotten an incorrect answer. It'd have to be this for it to be correct, I think. Yeah. Okay. Any questions? That? Okay. Oh, and the other thing is, so for the people who were in the room when I was discussing this at the end of the dynamics quiz and then asking about how it worked, this box isn't in free fall. If it's in free fall, its acceleration is 9.81. But the fact that the rope exists causes a resistance from the tension. From the tension of this box, if that makes sense. So that's why you can see that this number is not 9.81 downwards, right? Okay. All right, let's talk about rigid bodies, everyone's favorite part of this course. So let's think about like the nature of objects. This is going to get a little bit abstract, right? So everything that we've been talking about for dynamics in this course so far has been particle dynamics, right? And I don't think I've fully gone over what a particle is. So a particle is it has a point in space, right? And it can have a mass, it can have an acceleration, it can have a velocity. That's what we've been calculating so far. But we've been approximating things like cars, aeroplanes, whatever as a particle, right? And this assumption can only hold true if this particle doesn't rotate. Okay? So essentially if this car only moves linearly, right? Like not linearly, it's not a good word. Okay, let's think of another example. If we have a rod, right? And it's spinning about this axis like that, right? It has two components. It has from its center of gravity, it's moving like a particle, but it also has that rotational motion as well, right? So that's what we consider a rigid body. A rigid body has not only translation, but rotation as well. So I'll give you some examples. Oh, I've actually already drawn it here. So a rod is an example of a one-dimensional rigid body. Like we assume it to be one-dimensional essentially. Like we don't care about its thickness necessarily. We just care about the length, right? And so in the first part of the course, you might not have noticed it, but for beams are actually 1D rigid bodies, right? Where you can take the moments, the moment equilibrium of a beam, because it actually bends, it actually moves like a rigid body, not like a particle. But it gets a lot more complicated when we're talking about the dynamics of rigid bodies rather than the statics of rigid bodies, because you'll see like once you introduce like kinetics to rigid bodies, it's a lot harder to calculate than when it's not moving, like a beam or a column's not supposed to be moving. An example of a two-dimensional rigid body might be like a rock or something like this. So if this rock is like balancing on this point, and you can imagine it like tipping, right? This is kind of its like lever arm almost, right? And it's yeah, lever arm to its center of mass, and then it's tipping over like a cliff or something, for example. So that would be something with 2 dimensions from what we're looking at it from. Like it's 3-dimensional, but yeah. But its motion is 2-dimensional, right? Okay. Any questions regarding that so far? Okay. So basically, we have 2 components of plane motion. We have the translational motion, which I mentioned, like a car, for example. You know, it translates, but it doesn't necessarily rotate, like approximately, right? Something which rotates but doesn't translate, right, is something like a windmill, right? It has a fixed axis that it rotates about, but it doesn't actually move. Like this windmill's not moving up, down, left, right, whatever. So that's an example of something which has rotation about a fixed axis. But general plane motion, right, which makes up the majority of things that are moving in real life, is actually quite complicated, right? And it's a combination of this translational and rotational motion. And that's exactly what we're going to do today. So yeah. Okay. So let's talk about velocity dynamics. I just dropped like 5,000 things on you. But let's break it down one thing at a time. So what we're analyzing is this. This is a rod about a fixed axis. And we're saying omega here is its angular velocity. So you can imagine like, if this was like an animation or something, the rod might be like here and then it's moving that way, right? So we're calling this point here, point O. So this should ring a bell from like the statics part, where we have like a beam, and we have like, a beam is defined by 2 points, right? So this rod is defined by 2 points. It has this end, which we'll consider the fixed end, that doesn't move, right? And we have the free end, essentially. And this has a linear velocity of VA, right? And this motion has to be perpendicular to the length of that rod. So we call the length of that rod ROA. Sometimes it's also called OA, the hat, something like that, right? But yeah, it has to be perpendicular. It has to be 90 degrees. So if it was turning the other way, so like clockwise, the direction of this velocity arrow is perpendicular but the other way. The other thing is that, and this is easy to forget, but like it's pretty often that for a rigid body kinematics question, if you have multiple members connected to each other, like that for example, right? You have to generally start at the fixed end of this member, because that's where you have information. You have the information of the fact that it's literally not moving, right? Okay. Another thing which, I don't know, some of you might have been in my labs for the 1300 assignment. But I might have briefly mentioned that we use the right-hand rule to imagine the 3D like angular motion that's happening in the z-axis using the right-hand rule. So, okay, what do I mean by that? If you point your hand like this, basically, the rotational motion is going this way, but if you want to think of it like in 3D, the rotation is happening in the z-axis, and that's the positive direction. So counterclockwise corresponds to the positive z-axis, like that. And if it's the other way around, if it's going clockwise, right, then it's going into the page, and that's the negative z direction. Yet it does actually come up later in dynamics, sorry, in acceleration dynamics.
Is that just like a notation, like out of the page is positive, into negative, or is there like actually some sort of moment coming out like something?
It's not moments, because in kinematics we're talking about velocity, acceleration, that kind of stuff, right? It's just because if you remember when we took the sum of the moments, we took counterclockwise as the positive direction.
Yeah.
But counterclockwise is just a concept that only exists in 2D. The positive direction for spinning, I guess, anything spinning like angular velocity, angular acceleration, or moments is out of the page. So the counterclockwise corresponds to out of the page. And we just never thought about it before because we've only analyzed things in 2D. Yeah, hopefully that makes sense. So any rotational thing that's mapped on a page that we take counterclockwise is the positive notation. It's actually going out of the page. Yeah. Hopefully that makes sense. Yeah. So we have some formulas here. We're saying the angular velocity omega over A is equal to the velocity of A relative to O, right? And here I've actually scratched it out because O doesn't move, and so the velocity of A relative to if you're observing from O is just the actual velocity of A, right? So that's the kind of logic you're following if we're working from a fixed end, right? Here's another equation. It's just rearranged. It's just for the velocity is equal to the acceleration times that lever arm, or I don't know, the rod length, I guess you can call it. Does anyone have any questions of that? Basically, for velocity dynamics, I prefer to do the relative velocity method and thinking about it in terms of how it would actually move. But once we reach acceleration dynamics, it should be after the break. I just do everything by the unit vectors way, which you'll see. Because, I don't know, I can just more consistently get the answer, so that's why I do it like that. Okay. So yeah, I'm gonna move on. All right, so think about this system, for example. Basically, we have this little slider going to the right, and we have this little slider going down, right? And this is the snapshot of time that we care about. We have this rod which connects them, and we have like these angles that are formed in this right angle triangle between them, right? So, is this, what type of motion is this? What type of plane motion is this? Relative. That's how we're going to solve it. We can analyze it from the perspective of, okay, so A is going to move relative to B, or B is going to move relative to A, right? So you're on the right track. But in terms of the types of plane motion, we have translational motion, purely rotational, or general plane motion. So what kind of rotation is this rod? Sorry. So it's translational. If we mapped the like center of gravity between the current point and then if I moved it like 1 second later, it does translate. Like that center of gravity does move, but it's in general plane motion because it also rotates. Right, the rod is actually rotating over time. So like maybe the next snapshot might look like that, and then like that, and then whatever, right? So it's in general plane motion if both things are happening at the same time. I point this out because in the previous case, this one, we don't have general plane motion. Well, relative to this at least. We just have rotation about a fixed axis. Right. Yeah. Okay. So once we have general plane motion, we have to utilize relative motion where it's moving relative to something else that's also moving, basically, right? So the 2 points are moving relative to another object that's moving. That's basically what I'm saying, right? Okay. So I'm talking about it very generally because right now it might not make very much sense until we plug the numbers in and see a question. But yeah. We're going to have a component for translation and we're going to have a component for rotation. And it looks kind of like that, but yeah, like I looked back at these notes and I'm like, what the fuck is I even writing? Like, I might as well just show you how it looks like in a question. I think it makes more sense. Sorry if you're copying that down. Like, you won't get much out of writing it down, I reckon.
Straight cursor there.
Okay, but let's recall that relative motion for particles because it's going to behave pretty similarly, but the ends of each of our rigid body, like like rods or whatever, they're going to essentially act as our particles that we're looking at, right? So if one end's called A and one end's called B, our particles are like the ends of the rod, like A and B, right? So if you remember, the formula was velocity of A, something like this. Let's forget it. velocity of A is equal to velocity of B plus velocity of A relative to B. Okay, so basically, if I map out a triangle for VA, right, it goes from that point to that point, and then the right-hand side we can map out separately. So if the velocity of B is like this, right, once we add on that second component on the right-hand side, it should bring us to the same point as, like, the left-hand side of this equation should bring us to the same point as the right-hand side of this equation, right? Okay. So yeah, and so relative motion, if it's like a right-hand triangle like this, you can solve it using our understanding of sine and cosine. So sine and cosine are actually the easier version of how to do these angles, believe it or not, because sometimes you have to use sine and cosine law. If you remember what sine and cosine law are from year 9, I don't know. Yeah, from year 9, you basically never have to use sine or cosine law ever again up until now. So, surprise. But basically, just to give you a reminder, you use sine and cosine law whenever you don't have a right angle triangle, right? So for right angle triangle, one of our corners is equal to 90 degrees, right? But sometimes they're not equal to 90 degrees, in which case you'll have to use one rule or the other. So the sine rule is useful. Usually you either do like these two together, or these two together, or these two together, right? But it's useful for when you have either a missing side or a missing angle, right? So let's bring C out of the picture here, right? So say we are interested in finding one of these 4 variables, right? So either one of the angles or either one of the corresponding sides of the triangle on the other side. If we have 3 out of these 4 components, we can use the sine law, and it gives us the 4th component, right? But there is a special case where you're looking for an obtuse angle, right? So in this case, alpha is the obtuse angle, but sine law always returns the acute angle. It always returns the one that's less than 90 degrees. So use your understanding of geometry and don't get stitched up if you end up with the obtuse angle, because you'll have to flip it around. So you go like 180 minus whatever number you found for the obtuse angle. Yeah, any questions with that? This is just a reminder. You'll see how this plays into effect when we do the question. Cosine law as well. This one's useful if you... Slightly different. So it involves like 3 sides, 3 angles this time. But if you only have one of the angles, so like this for example, right? You can use this formula, right? But if you are looking for same thing. Okay, sorry. Basically, if you're looking for this, then you use this formula, but you have the other 3. Or if you're looking for this, then you use these 3. Right. So it's just a rearranged version of the same equation. Yeah. Yeah. Okay. I'm just going to continue. So here's our first question. All right. The first thing I want you to think about is, how is this shape gonna bend, like through its motion? Like, what will it look like in the next snapshot of time? Like, say, like 1 second later, right? Just you don't have to answer this, but just think about it in your head. It basically also says, by the way, it doesn't say it, but like, this is like a cylinder thing that extends this rod out, right? So the velocity of B goes in that direction because the rod kind of like extends out like that, right? Okay, so think about the other 2 rigid bodies, I guess, right? Like how are they going to move? How's member OA going to move, and how's member AB going to move? If you said something like this, you'd be right. Oops. Just doing that. Oh, anyway, yeah, you get the idea, right? Can't undo that for some reason. Yeah, it looked like that, right? Okay, so this is going to help because it's going to help us determine this direction of WAA. This is the angular, it's not W, sorry, it's omega. Omega OA is the angular velocity of this rigid body OA, right? And the order does matter. So OA means this, right? But this is AO. Do you know what I'm saying? So it's from the one that you're starting from, right? So if where you're looking at it from is O, then you write O first for the formulas to work. Okay, so here's what this looks like in this particular snapshot of time. I've just redrawn this. I've written it in meters instead of millimeters. But yeah, we're gonna call these angles theta, alpha, and gamma, okay? So what kind of triangle does this look like?
Not right.
It's not a right angle triangle. Don't get baited. This isn't right angle, basically. And so we're gonna need to use the sine or cosine formula later on. Okay, so let's just draw that again. And these sides do matter. Oh, I went through the effort of turning this into meters, and then I think it's better to do it in millimeters for now. Sorry, so these are in millimeters. These are the side lengths, right? Okay, so we have to work out these angles, right? And we essentially have three side lengths and none of the angles at the moment, right? And so would you use the sine formula or the cosine formula in this case? Very good. So you can't use a sine formula because it's dependent on the fact that you have at least one of the angles, right? Yep. So we're going to work out cosine. Oh, sorry. We're going to work out theta. That's this one here. Sorry, one sec. To BC. Oh, what am I doing? It's here. Okay. Oh, but I'm looking at the rearranged version of the formula, so I'm doing it on the fly. So this is the rearranged version of this, right? So we're rearranging for this angle, which is called C here, right? That's that. And the side that we've subtracted off is the corresponding side, the corresponding length on the opposite side of the angle. Opposite as in like that one, right? Okay. So this angle happens to be 28.3164 degrees. Okay, so that's that angle. We have to get the other angles as well, right? So I like to use sine law because it's way less annoying to write out. We just have to be careful of the case of the obtuse angle. Yeah, basically once we've figured out theta, we can find, yeah, we're working out gamma now since we have the information for theta. So I'm just going to color code this in blue and this one in purple, right? So that one's 90. So that one's that one's that, that's that, right? So rearrange for sine and get 43.248 degrees. Right, and the good news is we don't need to use the sine or cosine law to find the last one because we know that all of the angles have to add up to 180. So we just subtract off those other two angles from 180. We get 108.436 degrees. So there are all our angles, right? Okay, cool. So that's the year 8 maths part done. Going to make that a bit smaller, give myself some space. Okay, so now I'm just going to draw out our situation again, right? So as I mentioned, a good rule of thumb is generally you have to work from the node which isn't moving, right? So out of these, there's 3 rigid bodies here, 3 one-dimensional rigid bodies. We're going to analyze this rigid body first. So we're going to analyze that link. That's the word I'm looking for, sorry. So link OA is what we're looking at first, right? So I'll just draw it out. We're going to do it in meters here, so. Oh yeah. Oh, okay. Well, we've determined this is the direction of of omega OA, right? So its velocity is clockwise because of the motion which we were analyzing here, right? So because of that, this velocity arrow has to be going that way because it can only either go this way or that way. Do you know what I mean? So since it's not rotating counterclockwise, it can't be going the other way. Okay, so that's point A. Another, I guess, like important angle that you might want to, you know what? I'll draw it on after. I'll just leave it as that for now. So link OA, we know that the velocity at O is always fixed. You usually don't need to write this line of working, but it helps for my understanding at least. We're basically just saying this link doesn't move. This node of this link doesn't move because it's fixed, right? So now we apply our relative velocity formula like that because we're interested in this, right? We're interested in what this velocity is. But because this is 0, this is VA, I guess. So this will always be the case for when we have rotation about a fixed axis. Does that make sense? Maybe? Okay, cool. I'll take that as a yes. So whenever we see VAO, it's going to be the same thing as VA, right? Okay. So we're now going to analyze the next link, which is link AB. I'll draw that out. Oh, crap. Okay, but here's the catch. We actually have a bit of additional information from this end of this link, right? We know that this node B, has a fixed velocity of 0.6 meters per second, correct? So we're going to use that information to our advantage to work out velocity of A, and then go back and ultimately work out what this angular velocity was. So we know that that has to be 0.6 meters per second, and it's acting down because of how that hydraulic cylinder is constrained, right? Okay, and now we're actually going to be doing it this way around. We're looking from the perspective of B and then going towards A. So we care about this angular velocity, right? And we care about this, which is the relative velocity of A relative to position B, right, or like node B. And we know this has to be a right angle, right? And that's our position A, right? Okay, so we can express it like this, because again, we're looking for an expression for VA, because that's what we care about at the moment. And we know this is 0.6 meters per second. That's all we've got so far, right? Okay, but now we have a velocity triangle to build. However, I haven't drawn all the angles that we calculated in the previous step on necessarily yet. Okay, so here's where it gets trippy. So we've calculated that this angle, right? That's that angle there, right? Is theta. However, if you look, if you notice that this is perpendicular, and we split this off as if it's a right angle triangle, you can see that this is an equivalent angle of theta as well, right? And this is important because we're interested in this. We're interested in the velocity of A. So we need to see kind of what angle that that A is moving, I guess, because this is like diagonal movement, right? And we wanna kind of have this angle here, if that makes sense, right? So we just know that that angle there is theta. I guess similarly, we need to know what these. So we know this is gamma, right? Because of this, right? So that's from geometry. But again, because of how this is right angle, this also has to be gamma, right? And that's the part that's kind of like adjacent to that velocity that we care about, which is the velocity of A relative to B, in order to ultimately solve for the velocity of A, right? Okay, so this is going to become important in a second, because here's how I've drawn out these velocity triangles. Do you notice how I haven't drawn so this was like that, right? I haven't drawn out the angles in the directions of the lever arms, or whatever you want to call them, the lengths of the links, right? So these are the angles when they're relative to those radiuses. Yeah, so this is like the physical world, you know? We have these as like dimensions of our links, right? And these are the angles relative to them. But we actually care about like the velocity world, you know what I mean? And how the angles relate to those angles. Angles relate to those vectors. Yeah, that's what I'm looking for. You know what I mean? Yeah. Okay, cool. So let's build a velocity triangle out of these vectors in the velocity world, if that makes sense. Right. So we're gonna look like this. So VB goes down like that, right? That one's the simplest one. Okay, let me write out the bloody. Oh, actually, no, I wrote it here. So here are all the things we know. Here are all the components on both sides that we do know, and we're going to build a velocity triangle. So let's highlight that in orange, right? So this is the orange part. The orange part and the this one, right? The red part have to end up at the same point as the blue one, right? So this has to be VA/B. This will be VA/O, right? So here's this triangle here. Here's this one here, right? And I've drawn them out like this, you know what I mean? Okay. So let's look at that in terms of these, right? So this is what a velocity triangle is. It's the tip to tail of these two vectors together is equal to this. Oops. And now we've kind of created some sort of triangle, and this is going to help us determine the magnitudes of these things. Well, we know this one, right? But we actually use the sine rule here again, because if you notice, right, even though this triangle is not built out of actual geometric shapes, right? The shapes being things with like a length like r, they're built out of velocities. We can still use the sine law, because the sine rule just says for a triangle, when we know two of the angles and then we need to know, and we know one of these, but we need to know the other one, we can just use the sine law. Yeah, question.
Why are those two angles the same?
Sorry?
Why are those two angles the same?
Why are the two arrows the same?
Oh, sorry, I read it wrong. My bad. That one is alpha. Yeah, you're right. Sorry, my confusion. That one's alpha. So let's color code these, I guess, to help with the understanding. We're interested in the velocity of A, right? I know I said VAO, but we've established that VAO is VA because of that the fixed motion on one end, right? So this would be this, right? Which has this corresponding angle, and this would be this, and then this has this corresponding angle. You know what I mean? Cool. Okay. But yeah, this is actually what we solve for. So we can actually solve for the velocity of A relative to B, but that's not what the question's asking for. The question's asking for this, right? The angular velocity of OA, of like link OA, but this requires VA. So ultimately we're trying to find VA, not the velocity of A relative to B, right? So we can find that VA is this, right? And now we can simply plug it into this formula. Have I drawn it here? I haven't drawn it, sorry, it's taking a while. Right, so it's basically this, right? Since we know this in meters per second, right? This is why I converted to meters, by the way, because originally the question was given in mil, but yeah, we want to keep it dimensionally consistent. If you've noticed, this answer, right, it's in radians per second. I briefly talked about this like before the dynamics quiz, but radians are almost like unitless measurements of angle, right? So when you have something that's like meters, right, and you divide it by meters, yeah, this expression would be in radians, and then that per second stays as per seconds. Because actually degrees are easier to understand, like for humans to understand, I guess, but degrees are like its own unit, if that makes sense.
Yeah.
Yeah, so radians are unitless, so we want to keep it in radians. Yeah. Okay, any questions? Wow, that took ages. I'll give you guys a break. What was my plan? Oh damn, okay. I'll give you guys a break for 5 minutes. Go stretch your legs and stuff, and then we'll go through the next question. I have 4 questions I want to go through today. What's up, man?
The exam.
Yeah.
Sorry. Dane.
Sorry?
Dane.
Dane. Sorry, I'll take a second. Yeah, gotcha. If anyone else, sorry, if anyone else is looking for the test paper, just come up in front. How do you spell it?
Aiden is A-I-D-E-N. Lashawn is L-A-S-H-A-N. And then Karis is K-A-R-I-S. Yeah.
I'll look for it.
I was late, so I guess getting my paper.
What's your name?
Louis.
Sorry?
Louis.
Oh, yeah. Okay, I'll look through. Oh, I think I found it. This is someone else. Yeah. That's a recording. I'll talk to you like outside if you want.
12.
Yeah. I'm there.
8 to 11.
We'll talk outside of that.
Yeah.
When does term 3 go back? Something days. Maybe only like first week of September, but I'm not sure if that's right.
September the 9th.
Set
9th of September is, that's not a week, that's like,
That's
that's literally like week first week.
I just say the 18th.
when you take the
How would you see it?
What day is that?
You get 1 week in the SO week, and then you're back to it, you get 2 weeks.
Yeah, it's fun to see. Like this
Yeah, I've got my last
going
exam
down
very last day.
yeah, it's good.
There's just fucking people earlier at UC that they get like 3 months off in the end of the year.
So this is the
It's like, you get like a flex week plus another
then
week
they
section,
do get
like 2 weeks. In total, you get 3 weeks holiday.
And then next week they're like, oh, we got to study. And then we're also we go to a week later, we go to like Southern September.
because
And they're already got, my brother's usually goes to Southern South this morning. And if they knock off at like in October, if they start in March.
Do we finish our degrees quicker though?
Another one.
So I
BBA is just equal to BA minus BB. So BA equals BA minus BB plus BB.
That's reasonable.
These guys.
Well, what's the pricing of our subjects? Less than that, you see.
By allowing 18 subjects, possibly by allowing students to know that they can squeeze in more students and get more subjects on.
Then it's also more. So, yeah, it definitely is more. Yeah, because then we'll still pay to do 8 subjects.
That's, yeah, that's a fun way.
Yeah, they are classes. But usually if you're
I mean, at least we're not doing 4 subjects. True. Kind of frees up a bit of space.
As stressful, but yes.
You just have. That's the. You got less phones as well. But that's. I have my brother's they
So no matter where that
6
is,
week terms and they
if that
do
bit
5
was there,
or 6
there,
of
or
them.
there, the what's the bit of the
They do 2 subjects per term.
it would just be, if you draw B and that word there, it would be that one.
Yeah, they do this other stuff like that. Yeah, they just.
Draw
They just and they go for it real quick. It's like in 6 weeks.
Yeah.
I feel like right now, 3 subjects is like that's something to do that
Right.
4. So last year we did like 7.
Last year was like full time, like planned out the whole year.
Yeah.
And then when that
Did you guys all graduate last year? I graduated 400 year old, so at the start of this year, so.
Very story.
Yeah, pretty much.
It's going up that way.
So you're on some wise.
Oh, not at all.
So, you're basically
Yeah.
you're basically doing a
Then you
single.
guys all 05.
And so B,
Oh, yeah.
B,
Yeah,
this
yeah,
is
should be negative.
this is
Okay,
B.
yeah.
It's like this.
But
Something else. Yeah.
You can generally like if you explain that to way, you might even bump up in the marks for sure. But I don't know, it's worth a shot maybe if you like to speak.
birthday was yesterday.
Yeah, if you don't mind, then that's
I
fine.
made this cheese.
But anyway, yeah, all good.
Her birthday was 13th of August. And she.
Alright.
Yeah, her birthday was August. Started
Oh,
school
damn.
a year earlier.
Alright, let's continue in the interest of time because I want to go through quite a bit today. Oh, sorry, I am going through this quite slowly, so we'll speed it up. We're going to go through another question. I'm going to do it a slightly different way. We're going to do it using, basically, generally, this is the more preferred method from students. It's the instant center method because it's a lot easier to understand. Alright, so here's how free body diagram, I guess, right? And we have this as the fixed end at A. We have this link, right, to consider, and we have this slider that's fixed to only move in the x direction, right? This time we're given that this rotation is 6 radians per second. Where to find? Ultimately, the goal is to find this velocity, right? So we're looking for the velocity of c, right? So let's do that. So here I've just redrawn everything, and these lengths are in millimeters. Okay, so we know that the rotation here, the angular velocity is 6 radians per second going counterclockwise, right? So would the velocity of B be going down and right or up and left?
Up and left.
Up and left.
Up and left. Because this has to be perpendicular to the length of the rod, so it's got to be going like that, right? Okay, so VA is going that way, right? I might redraw that because that doesn't look right angle. That's kind of worse. Okay, anyway, just imagine that's right angle. It's a disaster. One sec. Let's do it in purple. Okay, whatever. Pretend that's right angle. Okay, and then the velocity of c, which is what we're interested in, right? We know that it has to slide left to right. Because it's being rotated like that, it's going to be sliding left. You know what I mean? Sorry?
The velocity will be of the upper left.
Oh, you mean this?
Yeah. No. The one which is marked as VA. It will be VA.
Oh, yeah. That's VD. And then this is VC. This has to be going left because, right, if we think about how this rotation affects the entire system, our machine's going to be moving kind of like this, right? So C is going to move to the left and not to the right. Okay, here's where it gets really nice for the instant center method. So the instant center method is essentially finding where these 2 points both rotate about. Okay, so I'll just show you what it looks like. So you draw a perpendicular line to that point B. Yeah, to the point B. Yeah, like infinitely spanning, and same with C, up until these two lines meet, right? This is the instant center. So you can imagine it like a big lever arm, I guess, right? You have a big lever arm has like some angular velocity, right, between these 2 points, if that makes sense. So that's what we call the instant center. Let's call it D. Sometimes it's called C, sometimes it's called I by convention, but because C is being used as one of our point names, we're going to call it D. All right. So let's look at these angles, right? So that's 45 degrees, and this is 30 degrees, right? because we know the instant center is right angle from these lines, this has to be 60 degrees, right? Okay. Wait, am I tripping? Yes, okay, that makes sense. Okay, so bear with me for a second. This is 75 degrees because this is 45 degrees. Yes, and yeah, anyway, this is 75 degrees. If you think about it enough, it's 75 degrees, all right? So the remaining angle there is 180 subtracted by these two. So that gives 45 degrees, right? And now we have our instant center and these corresponding angles. Okay, great. Let's focus on that link that's not moving. That's this one. So A to B. We said, well, basically I'm just saying this is VB because it's the B relative to A and A is not moving. So this is VB, right? This is the radius A to B. And that is omega AB, and that's 45 degrees, okay? Yep, so VB is equal to omega AB, which we're given in the question, and we're also given the length of that member AB, right? It's basically 0.2 meters. So do 0.2 meters, and it's 6 radians per second, right? So VB is 1.2 meters per second. It's going up and left, right? Okay. So given that we know what this is now, we can easily calculate VB. We want to calculate, we're aiming to calculate this number here, VC, okay? And so we can do that quite simply by relating these lever arms, right? We do them in different colors. This one could be yellow, sure. Okay, so let's find these lever arms. You can find them using the sine rule, right? Okay. Oh yeah, sorry. I'm gonna write out all three. So let's do this one in orange. Okay, so this one is this known length, right? Which has this corresponding angle. And then RDC, that's this one, has the corresponding angle 75. And RDB has a corresponding angle 60, okay? So that's our sine rule. And we basically equate these two equations and then equate these two equations, right? And we get RDC and RDB, okay? So to recap, we got what, I'm gonna do this in green. We got VB, we got these radiuses, and now you can imagine it's quite straightforward in order to get VC. Right? We just need to find this. This stays consistent. This is what we call the angular velocity of D, right? Which stays the same for the angular velocity of DC and the angular velocity of dB. Does that make sense? Maybe? Okay. So, we have to find the angular velocity first. So that's this here, right? We figured this out in the last step. We figured this out in the step before that. So this is 1.9 96 radians per second. Okay. Which means what we're looking for, which is VC, now that we have the angular velocity, is simply a matter of multiplying it by the lever arm, which again was slightly different, right? So instead of 0.612, it was 0.683, but it has the same angular velocity. That gives 1.34 meters per second going to the left, and that's our answer. Okay. All right, any questions of that? So, yeah, generally, the instant center of rotation method is a simpler one to understand. Just remember, you want to draw a perpendicular line from the velocity vectors until those 2 points converge, and then they will have the same angular velocity from that instant center of rotation point. Does that kind of make sense? Excellent. Okay. Oh, do you guys need a second to write this? Oh, sorry, I see a couple more scribbling out. Okay. All right, so acceleration dynamics, right? So we just talked about velocity dynamics. Here's where it gets really fun. It's where we do the acceleration dynamics. And I like to do it using the cross product of unit vectors method. So as I said, with things that are rotating, like basically for vectors which are considered like counterclockwise, clockwise, such as the moments, such as angular velocity, such as angular acceleration, we can think of it using the right-hand rule of being out of the page or into the page, right? And so that's where this dimension comes in. So we've never really talked about k before, but k represents a unit vector coming out of the page, right? So just to recap, I is the x direction vector, j is the y direction vector, and now coming out of the page we have k, right? And when we do the cross product of these, they're going to give us these corresponding answers. And for the cases I've highlighted on the right, we essentially have a negative number. So the order at which you cross multiply, right? So I cross multiplied with j as opposed to j cross multiplied with I will make a difference here, right? It will result in the same number, but the negative version. Okay, so when we want to answer like acceleration dynamics questions, right? So finding like the accelerations of certain points, for example, we have to do the velocity dynamics part first, which is what we covered in the last two questions. After we do that, we can start applying these kind of concepts. It's basically similarly, acceleration of A is equal to acceleration of B plus acceleration of A relative to B. So this is like, instead of relative velocity, we have relative acceleration going on here, right? But this relative acceleration component of A relative to B can be broken down further. And it can be broken down into its tangential component and its normal component. Sound familiar? Okay. So these have different corresponding formulas. For the tangential component, we have the angular acceleration, which is denoted by alpha, cross multiplied by the lever arm, right? But the normal component is the angular velocity squared dot product by the lever arm, okay? Just keeps getting funner and funner. So here's another way to, what I've done here, the only difference between these two is the first one I said velocity of A is equal to velocity of B relative to A relative, velocity of A is equal to velocity of B plus the velocity of A relative to B. For the second one, I said the velocity of B is equal to the velocity of A plus the velocity of B relative to A. So I've just swapped around like which velocity, like the end that we're looking at essentially, right? Okay. Oh, is anyone still copying that down? Most of you have given up. I like it. All right. So let's do this question. This is like a 1D rigid body, and it has two rollers on either end. So you can think of it like this is rolling down this way. This has like a fixed path that has to roll down that way due to gravity, right? But this question involves acceleration as well. So I'm gonna very quickly go over the instant center method again. So again, if you imagine the velocity going like that and the velocity going like that, the instant center will be here because these have to be right angle, right? And basically this angle has to be 60, this angle has to be 60, therefore this angle is 60 and all of these radiuses are the same. So it's 0.6 meters, okay? Let's call the instant center point C this time. This is point B, okay? All right. Oh, sorry, and it's saying that particle A here has an initial velocity of 4 meters per second and it has an initial acceleration of 6 meters per second squared. Okay, so when we're doing our velocity dynamics, we don't actually care about this yet, like that's irrelevant, but we will need to use that part, okay? So angular velocity of CA, right, which is this one here, is equal to that. And that's 6.67 radians per second. And it's going, okay, it's going that way, right? And so essentially we're saying, yeah, we want the velocity of B, and that's gonna be this one, but it's gonna be equal, right? Because that's what the instant center method is. These two angular velocities are equal. Okay. So, what have I done? Okay. Velocity of B, right, which is what we're interested in, is going to be, sorry. It's going to be this 6.67, right, which we worked out, and then it has the same lever arm kind of situation, right? And so it's going to end up being the same velocity, but going down and right. So it's 4 meters per second. So basically A was going down 4 meters per second. B is also going down 4 meters per second, but the vector is pointed at a different angle. So it's going that way. Yeah? Makes sense? Okay. So now we're going to basically we've determined the velocity. Now we have to determine the acceleration of roller B. Alright, so AB. That's what we're looking for. So we can use relative acceleration formula, and we're going to break it down to the units and everything, right? So keeping in mind our notation, I'm just going to write it out like this. Unit vector I is going to be the x direction, unit vector j is going to be the y direction, unit vector k is going to be coming out of the page, right? So acceleration of A, right, so that acceleration there, it's going to be negative 6j, and that's because the acceleration of A is pointed downwards, right? Okay, now we're going to split up acceleration of B relative to A into our normal component and our tangential component, right? I'm not sure if I said that in the right order, but it's going to look like this. That's the formulas I was talking about earlier, right? And we worked out this. We worked out this is the same as, oh wait, did I do this right? Oh, sorry. We can prove that the angular velocity of A relative to B, that's this one here, is the same because it has the same lever arm, right? So this is the ratio, right? So WAB is the same because these lever arms are the same. Do you know what I mean? Yeah, 0.6 on both sides. So that's this, which is this, right? So that's 6.67 radians per second. Yeah. Okay. I'm not going to plug in these until the next line, because if you look at what we're referring to, right? So did I write that right? RAB, sorry. RAB is this, and they're both RAB. Anyway, A to B. Think about this for a second, right? A to B. You have to think of it, the radius, as a vector, and it's two-dimensional, right? We have to break it up into its I component and its J component. It's going to be positive I because it's going to the right, and it's going to be negative J because it's going downwards, right? Or whatever. Okay. Oh, this is going to take forever to write. In the interest of time, I'm going to, sorry if you're copying this down, I'm going to show you what the steps look like. Fuck. You know what I mean? So here's the R, right? It's the exact same thing, but this component has to be cross products, right? And this product can just be dot product, right? Here was omega squared, yeah. And the acceleration of B, right? Which, remember, acceleration of B was just this kind of angle. We don't know the magnitude of it, but we do know the direction because it has to follow that path, right? So you can break it into that angle, sine and cosine. And we also don't know what the angular acceleration of AB is. But for K, if we're cross multiplying K and I, we get a positive result. If we cross product K and J, we get a negative result. But the net answer ends up being positive because there was already a minus sign here. Right? Minus sign, plus sign. Right? For those in the recording.
Like, where did the first minus and the second minus?
Yeah, so this is based on we know that AB has to follow that direction because of the hill being like this. So we don't know what that diagonal is, but we do know that this component and this component are like related through sine and cosine. Okay, basically, just follow my working. We expand everything out, right, after we do the cross-multiplying situation. And then these two group together to form 17. And then we have to compare the J and I components, right? So this is the I component on the left. These are all the I components, right? And then that results in these constants, right, in front of it. In which case we can use those to solve for AB. But we can also solve for the angular acceleration by comparing the J components, right? So these are the J components, right? Or rather, this and this, right? And then that results in this expression here. And since we already worked out the acceleration of B, and this equation has two unknowns, which is the acceleration of B and the angular acceleration of AB, then we can work out the angular acceleration, of BA. Yeah. Exciting stuff. All right. Does anyone have any questions? Right, even I have questions, as if you guys don't have questions. All right, let's move on to statics, because everyone loves statics.
Wow.
It's like a breath of fresh air. Okay, so let me just quickly give some advice about what I think will be in the finals. So your finals will probably be broken up into 6 questions, right? So the first question will probably be something easy, like a beam and a bending moment diagram. But in the 2023 paper, they got kind of stitched up because there was a triangularly distributed load on it. The second question will probably be a truss. And it was method of joints last year, so it was alright. But practice method of sections just in case. Question 3 was a frame bending moment diagram, which is what we're going to be running through right now.
Yeah.
Question 4, I can't remember, but it could be any number of things. Let's just say momentum, because they didn't test momentum in the test, in the dynamics quiz. And they also didn't test, let's call that impulse momentum. They also didn't test work energy. So that could be something that's in the test. These are for particles, right? The last question, almost always, is a rigid body kinematics question, which is the hell that you just experienced. Yeah?
With rigid bodies, like, does the angle stay the same when it rotates? Like,
Oh,
like, do you stay the same?
are you talking about, so if we have like something like this, right?
Yeah.
This is always perpendicular, right? So in this case, it would be like that. If the arrow was the other way around, it'd be like
But like, if
that.
we have two rods connected and they're rotating,
No, that angle can change. Yeah. Yeah. So like, let's look at an example of what you're talking about, right? This angle changed, right, between those two links as it moved through time. But we only analyze one snapshot in time, but that angle can change over time. Yeah. That's probably not as clear as this one. This angle definitely changed, right? So this to this. Right. They're like, one way to think about it is they're like pinned connections. They're not rigid connections, you know what I mean? Yeah, anyway. Okay. Let's do the question. All right, so forget everything you know about dynamics for the moment. We're gonna do some classic statics. So what's the first step we need to do when we're analyzing a beam or a frame? Very good. First step, always find the support reactions. I'm gonna skip that because I'm pretty sure you guys are pretty comfortable with that. But I'll give you the magnitudes. And we solve this using the equations of equilibrium, if you remember. So we can use sum of the forces is equal to 0 in the x direction, sum of the forces is equal to 0 in the y direction, and we can take the sum of the moments at whatever point. Right? That's how we do it. Yeah, just one question. Okay, I thought I saw someone's hand go up. All right, so we're interested in finding the bending moment diagrams, but for the sake of this question, I'm also going to show you how to do the axial forces, and I'll show you how to do the shear forces as well. But the question in this finals in particular was just the bending moments, so don't overdo it like I'm about to do it, essentially, right? But yeah, once we found those reactions, for a frame, we pretty much always have to do the algebraic method. You can't cheat and use the graphical method anymore, pretty much. Okay, so the first thing we're going to look at is this cut. Let's call this cut AB, okay? So this is everything happening basically around here, okay? So we're saying that between 0 and 5 meters, right? So x is equal to 0 here, and x is equal to 5 here, right? The beam's gonna behave like this, right? So we're gonna derive a function for that. Here I've drawn out all of the, what do you call it? Yeah, the internal forces, that's the word for it. Oh, it's been a while. Okay. Including the axial force, which I don't normally draw this one out, but it will help to plot an axial force diagram if you ask for that. So yeah, just remember these are the positive conventions for the internal forces. And we have this variable distance x, and we solve for the support reactions, which are these ones, right? Okay, so let's start with axial forces. This is the easiest one. We have n, but we also have 10, okay? So just have a think about this. Is this member, AB, being pulled, like in tension, or compression? Very good. It's being compressed. So here, that 10 is going to the right, and so the whole member squashes together. And when you solve for n, it gives you negative 10 kilonewtons, which is the correct convention that we're looking for, right? So negative number should result in compression. Okay. Next, we'll do some of the forces in the y direction. And this will help us solve for our shear force, right? So our unknown shear force is V, but we're going to do negative V because of the left-hand notation. And then we have our support going up like that, right? And what other forces do we have to consider in the y direction? Yeah. Distributed load, exactly. Is that just going to be 2? Is that just going to be 2? Very good. So 2 multiplied by x, because the magnitude of that distributed load is going to increase as we increase x, right? It's going to have a bigger and bigger load as we scan along the beam. We rearrange for V, and we get this expression. So this expression gives us our first variable. Yeah, I mean, you can say kilonewtons if you want, but like, yeah, we usually don't include it. So now we have a function for V, okay? All right, so now we're going to do the moments, okay? So we always take the moments about the cut to get here, right? I've called it mx for some reason. I guess it's because this point is where x is that we're analyzing. Let's call it mx, sure. So yeah, it's going to be counterclockwise, right? So counterclockwise that way. So that's going to be positive, right? What are the other moments, induced moments from the forces acting here?
Is the reaction of the support.
Very good. Are you talking about this reaction or this reaction?
Well, the 10 would just be 0 because it's going straight.
Very good.
But 5 points.
Very good. So we, yeah, basically that's going to create a clockwise moment, right? Let me do all the color coding and stuff like that. So it's going to create a clockwise moment about this point, and that's also going to have variable distance x, right? So are we done? Yes, for this particular force. Okay, what about, like, what other moments can you spot? Very good. So this distributed load, is that going to be positive or negative? Very good. 2 multiplied by, if we have x, are we done here?
Nope.
So this is the magnitude, right? This is the magnitude. But what have we not accounted for? This is the lever arm. Because the lever arm from this force to our point for the support was there, right? Where is the lever arm for this distributed load? Very good. So for a uniformly distributed load, that's going to be x on 2. Yeah? So don't forget that lever arm when you're taking the sum of the moments. Okay? I'm going to run out of space. Mx, yeah, so you rearrange, you get this. Yep. Okay. Any questions so far? Okay, cool. So, next we're going to do BC. Okay, here's the thing. We have to take a new cut whenever our function is disrupted, I guess. So the way that I like to think about it is, imagine there's our little stick figure guy, he's walking along, right? And we have like one expression for when there's a uniformly distributed load here. But as soon as that uniformly distributed load stops, right, there's going to be a new expression, right? There's kind of two ways to do this. It's one way you can consider x is equal to 0 to remain in this spot, right? Like that. Yeah. And then we go from x is equal to 5 to x is equal to 7. That's one approach. But I don't like doing that. I like doing it as a new x is equal to 0 here until x is equal to 2. Because this span of beam that remains is 2 meters, right? So we're going to go from x is equal to 0 to 2, right? So we have a fixed distance of 5 meters, right, which we've already crossed that part of the frame. And now we have a new variable distance x, which we're going to derive some functions for. It just makes more sense in my head this way, but you can do it the other way if you like. Okay, so now we have some new things to account for. Let's just do them a bit quicker this time. So we have the compression, which doesn't change. So n is still -10. We have the shear forces, -v. And here's the thing. We have this this reaction, right, of 5.714 like before. We also have a new point load which was introduced. Yeah. Okay. So we have this new point load as well. And we also have that distributed load which we have to account for, but now it doesn't have a variable distance, right? Now we know that the distributed load only acts over 5 meters. Okay. And so actually our shear force is going to be constant for this region of the frame. Do you know what I mean? So but it makes sense, right? Because if you're thinking about the graphical method, you're thinking about your shear force jumping up because of AY and then slowly falling because of that distributed load, and then it stays consistent when you don't have additional, oh sorry, there's another 10 going down here. So it actually look more like, jumps down by 10, and then it stays still. It stays still because there's no additional loads acting along this region, so it's a constant shear force. Okay, lastly, let's do moments, right? Some of the moments about the cut. Let's call that mx, okay? And now we have a couple of different distances to account for, right? So we have that support reaction on the left, okay? So what's going to be the lever arm of this support reaction? What's going to be the lever arm of this support reaction? 5.714.
X plus 5. Yeah.
Very good. X plus 5. Right. Okay, what about, well, this one, still no lever arm because it's acting through the line of action is acting through our point of where we're cutting. Okay? Okay. I did that the wrong, sorry, that's a negative, my bad. Okay, -10 is going to, sorry, we're going to do the other point moment, the point load, right, which is 10. Okay. What's the lever arm for 10 going to be? Very good. Okay, one more is going to be the distributed load now, right? how are we going to do the distributed load? Firstly, it's going to be positive because it's going to spin counterclockwise, right? How are we going to get the magnitude?
Half of 5 and then plus x. Yeah, x plus
Oh, the magnitude first.
Oh,
The magnitude is going to be fixed.
yeah.
That's the magnitude now. Yeah. And then what's the lever arm going to be?
X plus 2.5.
Oh, yeah. Oh, okay, I see what you mean. Yeah. Good. Okay, I'll write it like this though. X plus 5 on 2. Yep. So we have this variable distance and then this fixed distance away. So that's where the 2.5 comes from. Let's leave it on. Yeah, so there's going to be a little bit of algebraic simplification that you'll have to do. You'll rearrange for mx, and you'll get this expression. Okay. But the bending moment's going to be linear between this region. Right, so before, if you can imagine, it was like a parabola for the bending moment. But here, the bending moment's going to change linearly, okay, based on that function. That function is linear. Okay, next we're going to do CD. So here's where it gets cooked. Basically, our stickman is going to keep walking on the same side, but it's going to start walking this way now. Okay? So we're going to consider a new variable distance. So this is now going to be x equals 0, and this is going to be x equals 5. Got it? And we're taking this cut here, which we're going to call cut CD, okay? Yeah? So now we have to analyze. Yeah, all good. So here's where like a frame is almost like a 2D rigid body. You know what I mean? Because you have to analyze this problem in 2 dimensions. Okay, so we're going to start with some of the forces in the y direction, but these are actually going to be our axial forces now, because do you see how even with the left-hand notation, the axial positive direction has changed? So instead of analyzing the force in the x direction for the axial forces, it's going to be the force in the y direction for the axial forces, you know what I mean? So we're going to do the sum of the forces is equal to y. That's going to give us negative n, right? And we also have this, right? We also have this, and we have this. Okay, that's everything. Yeah. So n is going to give us this number, which is our axial compression, right? So we have an axial compression in this member here. Okay.
Sorry, Andy, I've got to move.
Yeah, all good, guys. If you need to leave, like, just come. But yeah, I'm just gonna keep going until this question is finished. Okay. Next, we're gonna do the sum of forces in the x direction, and this is gonna give us our shear forces. So since we took the positive direction as going to the right, and again, we've just turned our head like that for the notation, right, to still be the left-hand notation. Then our shear force is going to be the positive direction to the left, like that. And we're going to add on 10, because that's that 10 there, which was previously contributing the axial direction. Now it's in the shear direction, right? And then we have negative 2x. So that comes from this new distributed load, which is acting that way. Okay, yeah, and then we rearrange for v, and we get this expression. Okay, and lastly, we'll do the sum of the moments about the cut. And yeah, so we're solving for this, and we have to consider all the forces. So that's this one here. There's basically a lot. We're gonna do this force first. The lever arm is set to be 7. right? So 7 because 5 plus 2, that. We have this one here. That's 10 times 2, right? It's added. And then we also have this distributed load here times 5, right, which is the magnitude. But then, it's... Yeah. Very good. So that 2.5 comes from here, and that 2 comes from here. So that's 4.5 total of that. Okay. And then, oh boy, fighting for my life for this space on the page. Yeah, and then we have negative 10x. So this comes from this, and x is the variable distance, right? So lever arm is x, and then 2x, x on 2 is for this one, right? Okay, lovely. That gives us mx is negative 25 plus 10x minus x squared. Got it? Yeah, so that expression is for the bending moments for this beam. I mean, not beam, I guess column, but it's part of the frame, right? Okay, sorry, I might just skip in the interest of time. Oh damn, did a lot of commentary. Okay, here's everything mapped out. Okay, and then I'll talk about it generally. That was the free body diagram. This is the shear forces, the bending moment, that's axial forces. Kind of just need to use, I've just collected all of the equations that you derived from previous parts. It won't take this long in your finals because they usually just ask for the bending moment diagram. You know what I mean? But in case they ask for the axial forces or whatever, like a more niche case, I've done it here, so it's a good question for practice, right? And then, yeah, I've just mapped everything out, and for some of these parabolas, you might just need to use your understanding of how to graph things. But yeah, that's what it looks like. However, if you look at the work solutions, they look a little different. They look like this, right? So this is called, basically, you take, sometimes you can see, like in your lab assignment, you'll see positive bending moments underneath the beam, because that's a better representation of how the beam will actually deform in real life. So positive bending results in like sagging. Yeah. So yeah, they flip it around. The other advantage of doing it this way is the graph like overlaps with each other less than the other way, which is like that. And I just left some comments in here that you can read through if you like. But just remember that unless you have point moments, right, your bending moments are going to start at 0 and end at 0. So A and D, it's going to be 0 and 0. And unless you have, and even when you turn the corner, your moments are continuous. And again, unless you have point moments. But this value here, 25, which is this value, 25, it stays the same amount of bending even around the curve. That's basically the same. That's basically it. So yeah, thanks for coming to my classes. Yeah.
Thank you.
We're good.